In this lecture, I'm going to talk about what to do with the phase angle time series that you extract from complex Morley wavelet convolution or any other method. Just as a quick reminder, the oscillation phase angle or the phase angle time series refers to the position along the sine wave. And what you can see here, there's two things that I would like to point out here. One is that the phase angle time series is independent of the power. So here the power is lower and then it goes up and then it goes back down again. And the phases are just kind of going along as they were, independent of power with the exception of zero power. So you can imagine when there is no power in the oscillation, then phase is undefined. If there's no length of the line in a complex space, then there is no way to define an angle between a line that doesn't exist and the positive real axis. But in practice in EEG data, partly because the brain is very complex and dynamic and contains frequencies at oscillations or activity, I should say, at many frequencies, and partly because there's also noise and other characteristics that produce these kind of broadband increases in activity. In practice, there's rarely a situation in EEG data where you will find a frequency band that has power that's so low that phase is not possible to define. But just something you should keep in mind. In theory, phase is possible to define only when there is non-zero power, and phase is independent of power most of the time, except in these rare situations when power is very small. Okay, the other thing, just as a quick reminder, is that the phase angles kind of turn back on themselves, which in this sort of rectangular manifestation of these phase angles looks like this sawtooth pattern. So if you want to know whether the oscillation timing, the timing of the oscillations, and of course the timing is embedded in the phase information, if the timing is similar across trials, this is sometimes referred to as phase reset or phase locking to a stimulus. So how would you quantify this? How would you measure if the timing of the frequency-specific activity is similar over trials? So with many of the other measures of brain activity that we use, when we want to know how similar they are over trials, we simply average them together. So with ERPs, we just take the time domain signal and average them over trials. With time frequency power, when we want to know the how similar is the time frequency power over trials, we just average them together at each time point. It's very simple. So you might think that we treat the phase values the same, that we just simply average the phase angles over trials at each time point within each frequency. Unfortunately, this is not really a sensible thing to do. It's not possible to, or it's not appropriate to average phase angles together as if they were normal numbers on a linear number line. And that's because, as you know, these angles are referring to a cyclic measure that's cycling around this polar space. And so we don't want to average these vector lengths together, that would be the power. We want to average together, or we want to find the consistency of the phase angle between each of these vectors and the positive real axis. Here is the reason why it's not possible just to average phase angles together as if they were normal numbers on a linear number line. Here I'm plotting two vectors. These are unit vectors, so the line is defined going from 0 to 1 for both of these vectors. But the angle I defined here to be 2 pi and here to be minus 0.1, and these are radians. So you can see on this polar plot here the two angles. So now, or the two vectors. Now imagine what the average of these two vectors would look like. So the average would be in the middle, and the line, or the length of the average vector would be, well, very close to 1, because these things are very close to each other. So the average would look something like this. The angle would be somewhere between these two, the angles of these two lines. But if we just take the angle of the average of these two angles, treating them as if they were normal numbers, we would get a number that's somewhere around 3. Of course, this makes sense because 2 pi is a bit over 6, and yeah, 0.1 minus 0.1 is close to 0. So the average should be a little bit over 3. But if we were to plot a vector with an angle defined by this average, then that vector, that line, would actually point somewhere out in this direction. It would be like this. And just visually, conceptually, you know immediately this doesn't make sense. The average of these two vectors pointing in this direction should not point in exactly the opposite direction. So this is just an illustration of why it's not possible to average phase angles as if they were normal numbers on a normal number line. So instead, what we want to do here with phase angles is not compute the average phase angle, but compute the average vector. So here I have 4 pairs of vectors, and you can see that the closer they are to each other, so here in black are the 2 vectors, and then this thicker gray line is the average of these 2 vectors. And the number here illustrates the length of the average vector. So these individual vectors are all unit vectors, so they all have a length of 1. This is a unit circle. And the average is going to be, well, necessarily less than 1, right? And so here you see the further away these 2 angles are from each other, the smaller the length of the average vector. And of course, the average vector is pointing in a direction that is in between the 2 vectors, which should make sense. So, and then of course this would be 0 if the lines were perfectly orthogonal to each other, if they were, not orthogonal, in plane with each other, pointing in the opposite direction. And so this is the idea of how we compute the consistency of frequency-specific timing over trials. So what we do is here have an example with 3 different trials. And here you can see the phase angle time series from the 3 trials. So what we do is take the phase angles at each time point, and we generate a distribution of those phase angles in a polar plane like this. Now, these 3 vectors here are unit vectors, so they have a length of 1, and the angle of these vectors is defined by the angle at each of the phase angle time series at each trial, and this would of course be for one frequency. So note that the length of the vector does not come from the power of the oscillations at each individual trial. So that means we are stripping the amplitude information out of the data, and we are only taking into consideration the angles, the phase angle time series at each time point over trials. Okay, so now we have this distribution of 3 angles corresponding to 1 time point over 3 trials, and of course in practice you have many more than 3 trials. And then we compute the average vector from these 3, and then we take as our measure of phase clustering, or the consistency of timing over trials in each frequency band, to be the length of the average vector. Okay, so let's see some of this in real data. Here we have, so I call this inter-trial phase clustering, so ITPC. Here we have, these are actual phase angles from data at 200 milliseconds at some frequency, I don't remember what. So there are 99 trials in this sample data set, so there are 99 lines here, 99 gray lines. And each line corresponds to a single trial at 200 milliseconds. And now the average, you can already imagine that the average vector is going to point somewhere in this direction, and the length of this is going to be 0.6, or is 0.6. Here at a later point in time, there is less phase clustering. You can see the phases are more uniformly distributed over polar space, and here the ITPC value, the clustering value of phase angles, is much smaller. It's only 0.09. Down here in these lower 2 plots, I'm showing exactly the same data, but in a slightly different way. This is just, you might find this histogram illustration a bit more intuitive perhaps than this illustration. So here we have the histogram of phase angles, and now this is circular, so you have to keep in mind that this edge is the same thing as this edge, so this is kind of wrapping around here. Same thing here. And you can see that in this example at 200 milliseconds, there is a very strongly non-uniform distribution of phase angles, whereas here at 800 milliseconds, there is a much more uniform distribution of phase angles. So we can think about what the null hypothesis would be here in this kind of analysis, in phase clustering analysis. If there is no consistent timing of the frequency-specific activity over trials, what kind of a shape of a distribution would you expect? Of course, you would expect a uniform distribution, that the phase angles are just kind of randomly scattered over time. It would look something like this, a uniform distribution. And if there is consistency in the frequency-specific activity over trials, then you would expect a violation of a uniform distribution, so a more non-uniform distribution, perhaps a unipolar distribution that looks something like this. And so basically our measure of oscillatory consistency over trials, or ITPC, is a measure of this lack of uniform distribution, or the extent to which the distribution of phase angles is non-uniform over trials at each time point within each frequency band. Okay. So the equation for phase clustering is simple. This is really just an adaptation of Euler's formula. So here is, actually I say equation, but this is the Matlab implementation of the equation. So here we have the phase angles, and again this is this would be a vector of phase angles at each time point over trials. So we take the phase angles and then we Eulerize them, so we go e to the ik. This transforms our phase angles to vectors in a complex space, in a polar plane. And you can see that there's no amplitude, so there's no m e to the ik, or the m is implicitly set to 1 here. And that means we are stripping away or ignoring all the amplitude values from the original data, only taking the phase angles or the timing information into account. Okay, so that's this part of the equation. That's the Euler's function, so e to the ik. And now we take the average of those phase angles, the average of those vectors, and then we take the length of the average vector. This is a very easy point of confusion to make between extracting ITPC and extracting power. Because when you're extracting power, you may remember you want to take the average of the lengths of the vectors, so that's mean ABS. But now with phase, you want to take the ABS of the mean, the magnitude of the average vector. So it can get a bit confusing here, but it's easy to tell if you made a mistake. Because what you want is to extract the length of the average vector, not the average of the lengths of the vectors. So you can imagine if you would have, in this plot, what would be the average of the lengths of the vectors? Of course, the average of the lengths of the vectors is 1. All of these vectors have a length of 1. So if you extracted their lengths and then you took the average, you would get 1. Now in practice, you are never going to see a phase clustering of 1 in real data, in part because there's noise, and in part because the brain is just generally not so perfectly able to phase lock to external events. So if you ever apply this formula or something like this and you get results that are all 1s, then you know that you have swapped the mean and the ABS value. We can also take this a little bit further. So the average vector can never be greater than 1, or the length of the average vector can never be greater than 1 because all the individual vectors have a length of 1. And what is the smallest value that ITPC could possibly take? Of course, ITPC could never be negative. It can never be smaller than 0. These vectors are all defined as having positive length. Vectors always have a positive length. It doesn't really make sense for a vector to have a negative length, although in some cases in geometry, you can attach a negative length to a vector, but that usually just means that it's pointing in an opposite direction. But in practice, vectors cannot have negative lengths, so the average of all positive things has to be positive. So if you ever see an ITPC value that is greater than 1 or exactly 1, or if it is less than 0, then something went wrong in your Matlab code and you should figure out what it is. Of course, ITPC values, if you compute them relatively, they could be negative. So if you subtract a baseline or subtract 2 different conditions, of course the ITPC values can be negative. All right, so here is the equation. So it's really just Euler's formula with the angles, no magnitude information, so all the vectors are set to 1. Then we take the average vector, then we take the length of that average vector. Here's an example of ITPC for some electrode, PZ maybe. You can see there's time and frequency, and now you can see a fairly broadband, really not very frequency specific increase in ITPC. When you see something like this, this is most likely a different way of looking at the event-related potential or all of the phase-locked activity in an electrode. So this is not something that you would really kind of comfortably call an oscillation, mainly just because it spans several kind of classical frequency bands. Anyway, so this is a nice looking, very colorful plot. And now let's see if we can produce it in Matlab. All right, so here we start with our sample EEG data. We define some frequencies. We'll go from 2 Hertz to 40 Hertz. Here we pick channel PZ, and of course you can change this if you like. Now running on with the wavelet convolution, we're going to have a variable number of cycles. Here, this is all old stuff actually down here. This is all old stuff. Defining the wavelet, running convolution, these are all things that you should know by now from watching previous lectures. Okay, of course, if you run it, it produces an error because line 49 is missing. So, if you would like, you can pause the video and see if you can compute ITPC by filling in line 49. If you get it correct, oops, I wanted this. If you get it correct, then you should see a plot that looks like this. All right, let's see. So the first thing we want to do is extract this variable AS, this is the analytic signal. This is the complex representation. So we need to extract the angles from this. And now this is a two-dimensional vector, two-dimensional matrix, and it is time by trial. So that's something we're going to have to keep in mind. So now we want to Eulerize this by saying e to the I k, where k are the phase angles. And then we want to compute the average of these. Now we want to average over the second dimension, which is trials. We don't want to average over time points within each trial. That doesn't really make any sense here. So, and then we want to take the length of that average. Okay, so let's see if this works. All right, looks very nice, and it produces the same plot that we saw in the PowerPoint slide. This next cell runs a very simple simulation that I wrote that I hope will help you understand how the intertrial phase clustering is related to the distribution of phase angles within this polar space. So the way this works is you define the proportion of the circle or the polar space in which to fill vectors. So here I specified 0.6, which means that 60% of this polar space is going to be filled with angles. And here I define the number of trials, the number of angles, the number of vectors that we are going to use to fill up this space. And here I generate random data. So this is uniformly distributed numbers. So this will produce 100 numbers between 0 and 1. And here I scale them up to 2 pi. So that's going to fill the entire circle. And then I scale them down according to this variable that I specified here. These parentheses here are absolutely not necessary, but I put them here just as an illustration that sometimes when you're programming, sometimes things that are not really necessary for the code are useful for yourself just visually to group things together so they make more sense. So I like this, yeah. So this, to me, sort of helps me visualize what this line of code is actually doing, even though the code would be exactly the same if we took out those parentheses. Okay, and then here we compute the ITPC using the same formula as above, although we only have the angles here, so we don't need to explicitly extract the angles as we do here. Here I also compute the preferred phase angle, so that's the same formula, just we use angle instead of ABS to get the angle of the average vector. And then I plot these here. Oh yeah, and this also with the subplots here, you can see that these two subplot commands are different. So this first subplot creates a 3 by 3 matrix, and we're going to plot this histogram in the fourth position. So this would be 1, 2, 3, and then 4. And here I call a 1 by 2 matrix and plot the polar plot in the second plot. So that would be 1 and then 2, and I'm plotting it here. This is just in here to show you how you can use subplots in different ways to create different size plots in a figure. Okay, anyway, you can run this multiple times. It will produce slightly different results. You can change the proportion of the circle that is being filled, and then you can see that the ITPC value gets smaller. We can set this to like 0.09, and now you can see the ITPC value is very close to 1, of course, because there's very strong clustering here. Now I have this simulation hard-coded to always delete phase angles from here, so starting from 0 and going down. So if you would like a bit of a challenge, then you can try to change this simulation code a little bit so that you can also define the direction in which this phase angle distribution is pointing. So it's not too difficult, so you need another line up here to define what the preferred phase angle should be, and then you'll need to add something to this line in order to basically shift the angles around in space according to the parameter that you specify. Okay. Let's see. So there's two other things I would like to tell you about ITPC. One is that ITPC, like most or probably all analyses that involve phase angles, are sensitive to the number of trials, to trial count. So here I have ITPC plotted from a data set with 191 trials versus a random selection of 20 trials of this 191. And you can see that in pretty much all cases, except for a very small number of time points here, basically the result with 20 trials is always larger than the results with 191 trials. And in general, this is true. The more trials you have, or I should say the fewer trials you have, the larger ITPC is going to be. Of course, at the extreme value, you have one vector which has a length of 1, and the average of 1 is, of course, 1. So this is something that you need to take into consideration when analyzing your data and creating your experiments. If you have differences in trial count, there are likely to be, or you might get artificial differences in phase clustering strength. not because of the experiment, not because of how the brain works, but just because of the differences in trial count. So if you have a difference in trial count between your two conditions of 60 trials versus 68 trials, this is not really something you need to be concerned about. But if you have a difference, of if you're comparing conditions with 20 trials versus a condition with 150 trials, then this is something you really need to be concerned about. There are a few strategies for dealing with this. Of course, the best thing is just not to design your experiment such that you have large differences in trial count. And this is something, as I mentioned, that affects pretty much all of the analyses that involve phase. Also things like phase-based connectivity analyses. The second thing I want to mention about ITPC is that it is exquisitely sensitive to timing, and therefore also to jitters or uncertainty in timing. Here I took the same data and computed ITPC and power from this electrode. Here in the right two plots is the same data, but I simulated a little bit of temporal jitter in the onset of the markers, the experiment triggers. And the jitter ranged between 0 milliseconds and 40 milliseconds. And so this is comparable to, if you have a 60 hertz monitor and your experiment has some uncertainty of two screen refreshes, you might get jitter of this magnitude. So you can see that the power isn't really affected very much by this change. A little bit, you can see there are some differences in the higher frequency dynamics, but mostly the power is pretty robust to these temporal uncertainties or temporal jitters. But of course, the phase values or the ITPC values are just almost completely obliterated by even less than 40 milliseconds of temporal jitter. So this is something important to keep in mind when you're designing your experiment and collecting data. If these kinds of analyses are going to be important to you, looking at the timing of these different frequency-specific activities relative to a stimulus onset or some other external event, you have to make sure that the timing of the markers in the data is really precise and very accurate. Otherwise, you might get no results just because of these really minor, jitters of a few tens of milliseconds. Okay, so that was it for this lecture. I hope you found it interesting. Now you know what to do with the phase angle time series that you extract from complex Morley wavelet convolution.